Echoes of Jesus. It's a book that looks at the New Testament part of the Bible. It addresses 3 common questions. I'm just getting something here. That a lot of people ask about the New Testament. For instance, how was it possible for people to have recorded down what Jesus said and did when he said and did it? A lot of people have the idea that everybody back then was illiterate. So the first part of the book addresses that question of literacy and the cost of literacy. The second part looks at copying of the New Testament. Many people say, well, whoever wrote it down, that had to be copied for a long time and it would have got distorted. And the third question really looks at, well, how do we know what it said in the first 200 years compared to what we've actually got? So that's its major brief. The book is now in Russian. The Arabic version is coming along, and there's more translations in the pipeline, which is very exciting. You can buy copies down at the back there today. One of the future sessions of this Seriously seminar will be looking at copying of the New Testament. And as with all Seriously talks, if you've heard it before, it does get refreshed quite greatly, so it'll be all new and novel. So Christyn, could you please come up?
Okay, hello all. So I'm doing a talk tonight, it's my first time, so I want to thank John for allowing me to come out and talk to you. So my name's Christyn. I'm going to be talking tonight about fine-tuning of our universe. And so yeah, I studied my Bachelor of Mathematics, graduated 2019, so I've actually really enjoyed learning a lot about this topic. It's really complicated and detailed, so yeah, it was really enjoyable to learn about. Yeah, so my hope for you tonight is that you'll walk away just a little bit more in awe of our universe and maybe even of our God. So if we go to the next slide. So what I'm presenting is primarily sourced from this book, A Fortunate Universe, Life in a Finely Tuned Cosmos. This is a brilliant book. It covers fine-tuning of the universe with so many different examples. And so I've just selected a couple which I found really interesting to share with you tonight. So the authors are both super intellectual. They're not Christians, but they have PhDs. They've published so many papers in fine-tuning and astrophysics and cosmology, so they're very well knowledged in this area. Okay, sorry. So before I begin, I'd like you to think about this quote by atheistic evolutionist Richard Dawkins. So it says, "The universe we observe has precisely the properties we should expect. If there is at bottom no design, no purpose, no evil and no good, nothing but blind and pitiless indifference." So this is pretty morbid, but I want you to keep this in your back of your mind for the rest of my talk, and just see if at the end you agree with this statement at all. So the truth is there are so many ways which our universe is fine-tuned. So you can talk about how atoms in your body are just so constructed with perfect detail. We're going to talk about forces and how they're just in the exact right region for our universe to exist. And we can go into the crazy quantum physics, which is so small, and we're only just discovering this now, and it's been around since the beginning of the world. Okay, so I'm going to spoiler alert my presentation, just because I think it's really important to consider the whole way through. So we're going to first go really small. We're going to go microscopically small and look at atoms. We're going to look at how they're the building blocks of life and how tiny changes to these atoms has major consequences all around us. Then we're going to go into forces and see how these atom connections are just in a sweet spot for atoms to bond, for volcanoes to erupt, and for the universe to not actually collapse in on itself. And after all that, we're going to come to the crux of the matter. How did this all come to be? And with everything that is in this book, I read the whole book through, but it all comes down to 2 possible explanations. Either we're part of a grand multiverse, and just by chance this is the one universe that came to be, or there is a designer or a creator God. So for those tonight who don't believe in God, I hope tonight just opens up some new possibilities to consider. And for those of you who do, I hope tonight is just a night to just sit back and enjoy and just be in awe of our universe around us. Great, we'll go to the next slide. So first we're going to just define what we mean by the words fine-tuning. So when I was looking into examples, the best thing I could find was a cake analogy. So when you're making a cake, you've got your ingredients, you've got your recipe, and if you add a little bit more flour, a little bit less milk, it doesn't really matter, you kind of get the same expected result, you get your cake. But say you just leave out all the baking powder, or you just put in way too much oil, you just don't get anything that looks like what you expect, and it's a complete disaster. So in essence, fine-tuning is the limitations or sensitivity of given parameters or ingredients to still produce the expected result. Or another way to put it is the contrast between a wide range of possibilities and a narrow range of a particular outcome or phenomenon. Another way to think of it is an old radio set. This is not something I was familiar with, but I think it's a really good example of fine-tuning. So basically you have your radio station you want to tune into. You have all these different frequencies you can choose from, but unless you tune into the exact right frequency, a very, very small window, you're not going to get the desired station you would want. Great, next slide. So we're going to go really small and say what makes us up as humans. So hopefully you'll remember from primary school that we're made out of atoms. Atoms are the building blocks of life. So we have 92 naturally occurring elements in our universe. We can think of these as 92 little different bricks that you can build anything and everything around us. So each of these blocks or atoms can be broken down into subatomic particles. Here we're talking about protons and neutrons and electrons. And for a long time, this is the most basic scientists thought we could go. They thought this was the fundamental. However, this turned out to be not true. We have super powerful particle accelerators, and we put these atoms in, and we found out that protons and neutrons can actually be broken down further into quarks. And so, as it turns out, quarks and electrons that we know of at the moment cannot be broken down further. So these are our fundamental elements of life. So I just want to explain this diagram on the right a little bit further. So scientists have actually discovered 6 different types of quarks. So we have the up, the down, the charm, the strange, top and bottom. However, only the up and down quark occur naturally. So we're going to be focusing primarily on them tonight. And then we also have 6 other fundamental elements called leptons, and the electron is one of them. And then we also have its cousins, the muon and the toron, and then their massless counterparts, the neutrinos, which are at the bottom. So in total, we have 12 fundamental particles that make up our entire universe. Tonight we're just going to be focusing on the up quark, the down quark, and the electron, as these are the fundamental ones. These make up everything we see around us. Great, so go to the next slide. So our subatomic particles are very small, and they thankfully all fit together neatly like a puzzle. So we have the electron with its -1 units of charge. We have the up quark with +2/3 units of charge, the down quark with -1/3 units of charge. So to make a proton, 2 up quarks and 1 down quark all go together, and this gives the proton a net charge of +1 units. And then to make a neutron, which has an overall neutral charge, we take 2 down quarks and 1 up quark, put them all together, and we get our neutron. So these 2 quarks and the electron make up everything we see around us. These are the true building blocks of life. And so if we go back to our brick example, these are like the sand that makes the brick, that makes everything around us. And if we're going back to our cake example, these are the 3 ingredients that just make up the best tasting universe, I guess.
So
Okie dokie. So now that we're all novice particle physicists, we're curious and want to know the what-ifs. What if these fundamental masses were different? What if we were to change some of their properties? And should we be okay? We're pretty hardy, we're pretty robust, we've just been through a pandemic, we'll survive, you know? But let's have a closer look. So the mass of the up quark is 4.5 times the mass of an electron, and the down quark is 9.4 times the mass of an electron. So it follows then that neutrons are slightly heavier than protons, and protons are the lightest particle to be made up of 3 quarks. So this is really important to note because particles are extremely lazy. A way to think of this is if you're in a shopping centre, you have your stairs and you have your escalator, you'll always choose the escalator. And why? Because we want to conserve energy. And in the same way, particles want to do the same. So heavier particles will always want to decay into lighter particles to reduce the amount of energy being used. So here we can think of Einstein's famous E equals mc squared. The greater the mass of an object, the greater the amount of energy being used. So although the proton on one hand is happy and content, it's at its minimal energy usage, so it is perfectly happy and dandy exactly where it is. The neutron on the other hand is not so happy. It just wants to conserve energy, and so give it 15 minutes by itself and the neutron will decay into lighter particles. So it'll decay into a proton, an electron and an antineutrino. But thankfully we have the strong nuclear force, which we're going to talk about later, and this holds some subatomic particles together to maintain stability, so we don't have to worry about our neutrons falling apart, thankfully. Great, so next slide. So what would happen if we were to change some of these fundamental particle masses? So if we recall that neutrons are lazy and are naturally unstable, if we increase the mass of the down quark by a factor of at least 3, every neutron will decay, even those in the nucleus. So this produces a hydrogen universe, and that is just a universe consisting solely of the element hydrogen. And we'd have one chemical reaction. So to put this into perspective, currently standing there are over 60 million chemical compounds, and in this alternate reality we would be down to just one. And that's all there would be, one element on the periodic table, one chemical reaction, and absolutely no life. Even worse though is a universe where we increase the mass of the up quark by a factor of 6. So if we think of magnets in primary school, like charges repel, opposite charges attract. And so with the increase in positive electric charge, every proton will literally fall apart and decay into neutrons, positrons and neutrinos. So here we're left with an even worse universe than before. We'll have absolutely no atoms, no chemical reactions and definitely no life. And on the opposite side, if we decrease the mass of the down quark by just 8%, this will cause protons to capture electrons in their orbit and form neutrons. So again, we'll lead to a neutron universe, no atoms, no chemical reactions, and definitely no life. So now we've looked into the quarks. Unfortunately, they're a bit finicky. They don't really like being changed much, so maybe we'll have much more luck with the electron. Unfortunately not though. If we increase the mass of the electron by even 2.5, by a factor of 2.5, everything will be out of balance and we'll be back to a neutron universe as before. Next slide. So this diagram here summarizes the effect of changing the mass of the fundamental particles. So the grey region is the area that supports life and has chemical reactions, and the white area all around it is just bad luck. There's no life there at all. So we're pretty lucky here. Our universe is the black dot right in the middle of the grey region, and thankfully so. We are very fortunate to be exactly there. But we also want to just have a look closer at the graph. So what's happened here is we've just used the axis on the graph to get an interesting region. So to actually put this into complete perspective and to get an impression of the smallness of the grey space, we would need to extend the axis to account for the largest quark mass we've observed. And to do this, we need to add 4 kilometers to the right and to the top of this graph. So this is crazy. I don't know if that you can imagine that, but just that grey region would be the only bit of life. Everything else would be white, lifeless region. And we could even extend the axis of this graph further to include the maximum mass limit of fundamental particles, the Planck mass. And to do this, we would need to extend the axis by tens of thousands of light years. So just to get this in perspective, just that tiny little triangle is the only region that gives life. So if we go to the next slide. So I tried to put this into perspective. I was trying to do the 4 kilometers on either side, but there was absolutely no image left. So this is just adding 30 centimeters to the top and the right. So if we think 30 centimeters of ruler length compared to 4 kilometers is just absolutely incomparable. So actually, to get a proper area, we would have to decrease the size of this picture by over 160 million times in area. So just think we are in that tiny, tiny, tiny area. Great. So I think we'll just go to the next slide. So there's a lot more to talk about fine-tuning of fundamental particles. We can talk about particle spins and quantum fields and the infamous yet highly mysterious Higgs boson, which could be talked about for ages. But I think quickly we'll have a 3-minute break, talk to people around you about what you've learned, and then we'll come back together. Thank you. Okay guys, I hope you had a nice break. We're going to come back to it. Okay, so before we get back into it, we're just going to quickly recap what we looked at to make sure we all remember it. Sorry, it's probably just to take some takeaway points to take home with you. So, found that the up, the down quark, and the electron are the fundamental particles of life around us. And we saw that the mass of these particles is really important. So for example, we saw that increasing the mass of the down quark by a factor of 3 introduced a universe made solely of the element hydrogen and created an unlivable and dull environment. And then we saw that increasing the mass of an electron by just 2.5, a factor of 2.5, gave us a neutron universe where there'd be no atoms and no life. And we saw that picture where we sit in a very, very narrow region that allows for life not to only exist but to thrive. And we saw that if these masses were deviated slightly, we definitely would not be here tonight, sitting here. Okay, so I've just got a quick video to get us back into the swing of things. So this is a small amount of magnesium and silver nitrate that have been mixed together. And we've got drops of water that are going to be falling down. So if you have a look for the shadow of the water at the back. Great. So we see the sensitivity of these compounds with 1 too many drops of water causing a massive explosion. And so in the same way, so many properties of our universe are incredibly sensitive, with even slight changes causing drastic effects. So go to the next slide, yep. So when we speak about forces, we're speaking about what animates us, what causes things to interact and cause motion. And although we expect there to be a lot of different forces at work, there is actually only 4 in everything we see around us. So 2 of these we see in everyday life, so that's gravity and the electromagnetic force. The other 2 you hopefully won't see in everyday life because these are at the very centre of atoms, and so this is the strong and the weak nuclear force. So gravity is something we experience every day. We think of Isaac Newton, the apple on the tree, we jump, we come back down. So gravity is simply the attraction of matter to itself. Gravity is super important. It's responsible for keeping planets in orbits and for stars having their stability and for planets to have and sustain life. And although it's probably the most talked about of the forces, there's still a lot of mystery around this and so many fine-tuning examples just in this area alone. But tonight we're just going to be focusing on the other forces, and then, we can come back to that if we need. Great, so electromagnetism can be explained by thinking about magnets. So it's simply, if we have like charges, they repel. If we have opposite charges, they attract. And the strong nuclear force, so that acts within an atom and to bind quarks together to form protons and neutrons and gives atoms stability. So this is a really important job. It's basically the glue of atoms. And then we have the weak nuclear force, which is responsible for a lot of really bizarre properties of the universe, but primarily is involved with radioactivity and nuclear fusion. So I'm just going to quickly make a side note. Don't worry too much about it if you're not catching on. I want to just make sure that I'm covering this. So particles feel force by way of gouged bosons or force carriers being emitted from a particle. So this is hard to understand at a large scale, but when we're looking at quantum level physics, everything comes down to probability. So when we're talking about the strength of forces, we are actually meaning how likely a force particle will be exchanged. So when I'm saying that when I'm saying one force is stronger than another, I'm actually saying that it has a higher probability of a particle emitting a force carrier particle compared with another. Anyway, don't worry too much about that, but just to cover all grounds. So we'll go to the next slide. So when we're looking into fine-tuning of forces, we're going to be primarily tonight looking at changing the strength of these forces, especially the strengths compared with one another. So we're just going to take the example and consider within a proton we have 2 up quarks. So we remember that they both have positive charges. So the rules of electromagnetism state that they should repel each other, that the protons should fall apart. On the other hand, though, we have the strong nuclear force, which binds them together and attracts them towards each other. So in the same instance of time, what is more likely to happen? Is the proton going to fall apart with electromagnetism, or is it going to stick together with a strong nuclear force? And so this all comes down to the strength of the forces. So the example I've got on the screen is just a bigger example. So here we're looking at an atom. The protons all want to go away from each other with electromagnetism, but are actually bound together with the strong nuclear force. So as it turns out, the strong force is almost 20,000 times stronger than the electromagnetic force, and so very, very lucky for us, we're not going to spontaneously fall apart. Our protons are very, very stable. But we want to think about what would happen if the strength of these forces were different. So go to the next slide. So as we've just seen, the strong force is super important for the stability of everything around us. This is the strongest of the forces, and thankfully so, otherwise the world would literally be falling apart around us. So if we reduce the strength of the strong force, atoms will start to lose their stability and will undergo alpha decay, where a heavy element emits the nucleus of a helium atom. This is really bad as one element will literally change into another element. and so alpha decay transmutes elements. It sounds kind of cool, sounds like a sci-fi movie, but unfortunately it's really bad. We would have molecules changing all the time. Our DNA in us would also be changing, and that would just cause a lot of complications. And in fact, even decreasing the strength of the strong force by a factor of 4, or mathematically this is equivalent to increasing the strength of electromagnetism by a factor of 16, this will eliminate all elements on the periodic table from carbon up. So definitely not a good time. No life would exist at all. So likewise, the electromagnetic force is sufficiently weak for chemical reactions to take place and molecules to form. If it was any stronger, protons in the nucleus would be unstable, leading to a universe full of neutrons, which we've talked about, and no elements. And if it was any weaker, chemical reactions wouldn't take place, and molecules wouldn't be able to form. So here again, we've got a picture. We are in that tiny, tiny kind of rectangular region of stability, and that little black dot is where our universe sits. So we are exactly positioned perfectly in a region of stability, and this is just a phenomenal place to be. Once again, we want to look at the axes of this graph, so it's not just what it looks like. The axes of this graph are actually logarithmic. So we have that the first section is 0 to 0.01, and the next section is 0.01 to 0.1. So every little section, we're multiplying by 10. So to put that into perspective, the area that looks like this big is actually tiny, tiny if we think of it on a linear scale. And so this goes all the way up to infinity. And so this is just another example. It's a fine-tuning work of art, how we are just exactly where we need to be when comparing the strong nuclear force and the electromagnetic force. Great, next slide. And so this isn't even the beginning of it. We've only looked at the two examples behind fundamental mass particles and the fundamental forces and their strengths, but this doesn't even begin to cover it. So we could look into the fine-tuning of radioactivity, how the Earth has the perfect amount of radioactivity to have a solid surface and still have shifting tectonic plates. So although disastrous and we have volcanoes and tsunamis, although this is really bad, it's actually really important because it keeps nutrients cycling through our biosphere. And it keeps soil rich and agriculture fertile, and without the flow of nutrients like carbon, complex life on Earth would not be possible. So if we had too little radioactivity, this gives a solid, dull, and completely sterile planet. And on the other hand, if we had too much radioactivity, we wouldn't be standing on solid Earth. The ground itself would be a molten surface, and just wouldn't allow for life at all. We wouldn't be here. So yet again, our Earth is very, very sensitive, and radioactivity is just another example of that. And we are very fortunate in that to be granted life as well. So we could also present the example of how all the fundamental forces are symmetric, bar the weak force, where every single neutrino in the entire universe rotates, spins in the clockwise direction. So this might not sound so cool, but I'm going to give you a bit of background to this. So all particles spin, and because of the symmetry of the majority of the universe, they can either spin clockwise or anti-clockwise. So if we take an example, we look at photons traveling from the sun, we can pick out a random one. Some of them will be going clockwise, some will be going anti-clockwise. If you held up a mirror to one, the reflection you see would still be something that is common and is allowed in our universe. However, neutrinos don't do this. All of them, none of them spin the other way, they all spin clockwise. And to put this into perspective, every single second there are trillions of neutrinos that pass through your body. So this is just an astounding discovery. So much so that this astounded scientist so much so that it received the fastest Nobel Prize in all of history. Just 1 year it got the Nobel Prize. And scientists are still struggling to understand and appreciate the meaning of this result. how do all these tiny particles know to spin one direction, and what does this mean to our universe? And so this is just a phenomenal discovery and shows the intricate details of our life around us. Another example of fine-tuning is that we're living in the ideal dimensions, 3 space and 1 time. It can be really hard to imagine life any different to this, but mathematically you can conjecture up different options and trial it out and see what happens. Fun for the mathematicians. So if we change the discrete dimensions of in either space or time, this will drive the universe to either complete chaos or to a universe that's far too simple for life to be born. So as one of the authors wrote, if our universe had been born with a different number of spatial or temporal dimensions than the 3 + 1 we currently inhabit, the prospect for complex life would have been severely diminished, if not downright impossible. So hopefully by now I've convinced you that this universe is extremely fine-tuned. There are countless examples of ways that things are just so intricately balanced and just perfect for life. So at this stage the authors come together and they say, how could this all happen? How is everything so perfectly balanced? And how is it that science is discovering and solving all these new mysteries? And it just seems like a game of catch-up in the end. This has been around for ages and we're only knowing it now. So the authors narrowed down to 2 possible explanations. Either we're part of a grand multiverse and this is the one universe that chanced the right conditions to survive, or there is a creator God. Next slide, yep. So unfortunately there's no single agreed definition of what a multiverse is. Some speculated along the lines of a many worlds idea. So here many universes are produced and this is one of the outputs. Others think of it as one gigantic universe with different patches of universe having different laws and different properties. So the primary thought behind all of this is that each universe contains a different mix of laws, masses and constants. As we've seen, most of these universes will result in dead, sterile and barren places with absolutely no life. So there's been a lot of thought put into these by scientists. Unfortunately though, there is no evidence behind any of this, nor will there ever be. This is an unobservable theory, and unfortunately scientific theories must be observable to be given any credit, and nothing out of this theory can be directly detected. So the argument can be made that we're just beginning to scrape the surface, or only beginning to discover the universe, and with enough exploration in time we might start to find the answer. However, a lot of multiverse theories are being scrapped and discarded, and the whole theory starts to look a bit suspicious. So much so that we might even have to fine-tune the multiverse. And so the multiverse theory, which sounds like it comes from science fiction, actually starts to look that way. The whole premise seems to be grasping at straws to kind of avoid a scenario that many don't even want to consider being true, that there is a creator God who intentionally designed this universe for a reason. So science is not in opposition to God. In fact, the very existence of God gives an explanation behind all of science. We can either believe in naturalism, which implies that physical stuff is the only stuff, or we believe in a God with clear intentions behind his design. So the main problem with naturalism is that it's dismissive. It does not answer any of the questions that science is actually all about. Yes, we have all these physical phenomena, then we know that they come from these ultimate scientific laws. But where do these laws come from? Why are these laws the way that they are? And to say that it comes from nothing is a blanket statement, and it implies that these questions are unanswerable and leaves it at that. Next slide. On the other hand, a creator explains the why behind its creation. So here the laws of nature are a description of how God runs the universe, and fine-tuning is like the finishing touches to the creation. If we consider the possibility that we have a good God, we expect God to create universes that have morally desirable qualities. We expect him to create a world that's perfectly designed for people he created and loved. And so a universe that is capable of producing and sustaining creatures with free will, who can do good and interact and influence and be responsible for others, who can investigate and see beauty and learn love and knowledge and truth. This is a universe of moral worth, and this is a universe that God would create. And so if we're totally honest here, we see that God creating the universe is really one of the only plausible explanations for the universe we live in. If multiverse theory is still on your radar, I just want to get you to consider this. It does take the same amount of faith to believe in the multiverse as it does to believe in God. And the few detailed fine-tuning examples we looked at really just scraped the surface. Actually, the further down into it you go, the more fine-tuning you see. It just never ends. So we just want to think about it. What are the chances that this all happened by chance? And for me, I do the maths and cogs will turn, and I just think, I don't think this is possible. But if we consider that there's a God and that he could create a universe, the chances that he would create a world that is good and is perfectly sustainable in everything it is, that just makes a lot more sense. And so, to quote one of the authors, only an extraordinarily strong presumption against the idea that God would want to create a universe with embodied moral agents will affect our conclusions. And so to conclude, we'll go back and consider Dawkins' quote, "There is no design, no purpose, no evil, no good, nothing but blind and pitiless existence, indifference, and we can now clearly see that this is just an absurd statement, and there is no credit in it. We can see that the universe has been clearly designed with purpose, and following that we have been designed with purpose. And as Paul says in Romans, for since the creation of the world, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood from what has been made, so that people are without excuse." Great, so that's all I have for tonight. Hopefully you've enjoyed it, and we'll do a quick question and answers now. Thank you.